faster-than-light travel? You know, it's the holy grail of science fiction. But what as I told you, the math to make it happen actually exists. So today, let's dive into the real and truly mind-bending science of the warp drive.
You know, we all dream of exploring the galaxy, right? Hopping between star systems like we're crossing oceans. But, well, physics has basically put up this giant cosmic stop sign. There's a universal speed limit, and it seems absolutely unbreakable.
And the guy who came up with this universal law? None other than Albert Einstein. His theory of special relativity, it created a barrier that seems to put the stars forever out of our reach. And make no mistake, this is a hard rule. As an object with mass gets closer and closer to the speed of light, its energy just shoots up, basically approaching infinity. It's kind of like the universe's way of saying, nope, you shall not pass. It really seems like a dead end for any interstellar dreams. But here's where things get really interesting. And get this, the guy who made the rule is also the one who, believe it or not, gave us a hint at how to get around it. The answer wasn't in his theory of special relativity, but in his other masterpiece about gravity, general relativity. So, what's the big loophole? Well, it's not about building a faster engine to just blast through the speed limit. It's much cleverer than that. It's about changing the road itself. It means we have to stop thinking of space as this empty, boring stage and start seeing it for what it is, a flexible fabric that you can actually manipulate.
Okay, so let's be super clear on this one point. The rule itself still holds. Locally, right where you are, nothing with mass can travel through space faster than light. Your spaceship, the astronauts, every single atom, they're all stuck with that speed limit.
And this is the light bulb moment. General relativity tells us that spacetime isn't static. It can be bent, it can be stretched, it can be warped. So what if you could create a wave in spacetime and just have your spaceship ride it? This totally brilliant idea was first laid out with real math back in 1994 by a physicist named Miguel Alcubierre. He proposed what he called a warp drive, basically a solution to Einstein's own equations that describes a bubble of spacetime that could carry a ship faster than light. So how in the world does this work? Okay, imagine you're a surfer. You don't swim faster than the wave, right? You just let the wave carry you along for the ride. The Alcubierre drive is kind of the same idea. It would create this massive disturbance that violently contracts spacetime in front of the ship, literally pulling your destination closer to you, while at the same time it expands spacetime behind it, pushing your starting point farther away. Take a look at this. You can really see the magic in action. See that deep well in the front? That's spacetime getting squished, pulling the destination closer. And that huge wave behind it? That's spacetime expanding, pushing the start point away. And the ship? Well, it's just sitting there, completely peacefully, in that calm, flat bubble right in the middle, just riding the wave. And just think about what that means for the people on board. Inside this warp bubble, the ship is just coasting in its own little pocket of normal, flat spacetime. It's not moving, it's not accelerating, it's basically at rest. That means passengers wouldn't be crushed by insane G-forces. And this is the incredible part, they wouldn't experience any time dilation. Years wouldn't fly by back on Earth while they're gone for a week. And because the ship isn't locally moving, Einstein's cosmic speed limit is never actually broken. It's genius. Yeah, this all sounds absolutely fantastic, doesn't it? Almost too good to be true. A way to explore the stars without breaking physics and without all the weird time travel headaches. Which, of course, leads us to the big question. What's the catch? And yeah, it is a huge catch. To create this kind of insane space-time distortion, this wave, you need to power it with something. And that something is where this beautiful theory smacks right into a massive physical wall. To bend and stretch space-time like this, you need a very special kind of fuel. A fuel with properties that seem to just completely defy the laws of physics as we currently know them. It's called negative energy density, or sometimes exotic matter. The easiest way to think about it is like matter, but with negative mass. So where normal matter and gravity pull things together, this stuff would have anti-gravity. It would push space-time apart. Now, while tiny little flickers of it might exist at the quantum level, our current understanding of physics says that creating a stable, big chunk of it would violate some really fundamental rules about how energy is supposed to behave.
And we're not talking, a pinch of this stuff. The original math suggested you'd need a chunk of this unphysical energy with the mass of entire planets or even stars. So here's the bottom line. The math works out beautifully, but the ingredient list is, for now, completely impossible to fill. So if the Alcubierre drive needs an impossible ingredient, you're probably wondering, why do physicists even bother studying it? Why waste time on an idea that we might never, ever be able to build?
Well, the answer is that studying impossible ideas isn't always about building them tomorrow. It's about stress testing our most important theories today. It's actually how a lot of progress happens. I mean, Dirac's equations predicted anti-electrons decades before we ever found one. By pushing the rules of general relativity to their absolute breaking point with crazy ideas like warp drives, scientists can see where the theory might start to crack and maybe, just maybe, find clues that point towards brand new, undiscovered physics. Which leaves us with this one last thought. The Alcubierre drive, as we understand it today, really does seem to be a physical impossibility. But our understanding is always changing. This whole problem of the impossible ingredient forces us to ask really deep questions about what energy and space-time even are. And it makes you wonder, are some ideas truly impossible, or are they just impossible for now?